feel the vibe.
What's up, guys? Welcome back to another Algebra 2 instructional video as we start a new unit here looking towards rational functions. Before we get into rational functions, we're actually going to do a little bit of a focus on rational expressions. Most of this work is going to be a refresher from Algebra 1, but maybe scaled up a little bit to a little bit more intense of a level. And so we're going to review some concepts, go over some concepts, and maybe throw in some new concepts for rational expressions. So the focus here is going to be on arithmetic and simplifying. Let's first get into writing a rational expression in its simplest form. A rational expression, or a ratio, as you may remember from previous classes, is a comparison of two numbers or two expressions. Can be in a number of different ways, but commonly we write those as fractions. So we're going to start with simplifying. So let me give you an example. Let's say I have 12 over 9. And we want to simplify 12 over 9. And most of you can look at this and say, okay, that's 4 over 3. Well, really how we get there is by factoring 12 into 4 times 3, and factoring 9 into 3 times 3, and noticing that these 3's would divide out and become 1, and therefore giving us 4 over 3 as a simplified version of the ratio. This is essentially the process that we want to do with rational expressions. So I commonly see errors here in simplifying rational expressions when dealing with polynomials. The goal is to factor and eliminate factors. So we can write a rule for this. And so let's say that we're given P, Q, and R that are polynomials, and P and Q are not equal to 0. PR over QR is equal to P over Q. So the R's would cancel out, essentially what we did above with the factors. And we could also write that as a factor, a polynomial, a rational expression, P over Q, where we multiply both P and Q by R, and those would be equivalent. Really, what we're going to focus on is the first part of this, that if I can have polynomials that are going to be essentially factored and reduced, then I can eliminate common factors. So let's look at some examples. In problem number 1, it says write each of the following expressions in simplest form. So what we have is x squared minus 1 over x squared minus 3x. Commonly, what I see is people identify that there's an x squared in the numerator and denominator and cancel those out. This is incorrect. We cannot simplify terms. We can only simplify factors. Let me give you an example of that. Let's say I had 1 over 3, and then I had plus 2 over 1. So this would be like 1 plus 2 over 3 plus 1, which we know is 3 over 4. But if I canceled out the 1's, because those are being added, I would get 2 over 3, which is actually not correct. So that's the same thing that goes on with polynomials. So I cannot cancel out the x squareds. What I need to do is follow this rule. I need to factor and eliminate factors. So the first step here is to factor the expression. So we're going to see a review here of factoring, or we're going to bring back a lot of our factoring knowledge. In the numerator, I have the difference of two squares, x squared minus 1, which would factor into two conjugates. Hopefully we recognize this as x plus 1 and x minus 1. Then in the denominator, I can factor x squared minus 3x plus 2 into two binomials. The first term in each would be x and x, because that multiplies together to give me an x squared. I know the signs both have to be negative because they have to multiply to be a positive and through distribution add to be a negative. The only factors of 2 are 2 and 1. So once I have factored this expression, now I can look for common factors. And we can see that they do have a common factor. This x minus 1 is contained in both the numerator and the denominator. So I can essentially divide those to become 1. And the ending result would be x plus 1 over x minus 2. This would be the final answer. Again, I cannot cancel the x's because those are terms, not factors. So the only thing that can be divided are polynomials or factors of the original expression. So the simplest form of this expression would be x plus 1 over x minus 2. Eventually we'll look at what x minus 2 in the denominator means in terms of function, but for right now we're going to focus on the simplifying. So let's take a look at another example. In example B, we want to essentially do the same thing. So factor first. So generally, when we factor, we want the polynomial to be in standard form, so in decreasing degree. So what I'm going to do here for the numerator is I'm going to factor out a negative 2, and that's going to leave me with x minus 3. So if I take away negative 2 or divide negative 2x by negative 2, that gives me an x. If I divide 6 by negative 2, that gives me negative 3. Now again, why I took out the negative here is because I kind of want this in standard form, so decreasing degree. And generally, I want my leading coefficient to be positive. That's going to help us to figure out what factors are the same. Now, you don't have to do it that way, but it can sometimes simplify the division process. In the denominator, I may notice that I have the difference of two squares. So I can factor this into x minus 3 and x plus 3, the two conjugates, the roots of each term. Here I may notice that I have a common factor in the numerator and the denominator. So I can divide those, and those become 1. So this would be negative 2 over x plus 3. And this would be my simplified version. So if you kind of see what the process is here, we are factoring polynomials and then dividing out the common factors. So if you're feeling comfortable, go ahead and pause the video and see if you can complete C. And let's take a look at C. So again, the process is the same. The numerator I can factor fairly quickly with a GCF of 4. So this would be 4 over x plus 5. The denominator is going to take a little bit more work. So notice the denominator, we have 4 terms here. It's in a cubic polynomial, and so I'm going to try to factor this one by grouping. So if I group the first two, the GCF would be x squared, leaving me with x plus 5. If I group the second two, the GCF would be negative 2, leaving me with x plus 5. I can rewrite the denominator, so I have not changed the numerator at this point. It's going to stay the same, 4 times x plus 5. I did not change it at all in that step. The denominator now becomes x squared minus 2 and x plus 5. I could factor the denominator further, but in this case I don't need to. Only factor if that's going to help you simplify. In this case, I can divide out x plus 5, and it doesn't matter how I factor or how I would try to factor x squared minus 2. I would never get a common factor of the only thing remaining in the numerator as 4. And so I would leave this as 4 over x squared minus 2. And this would be my final answer. So the goal here is to factor and eliminate those common factors when simplifying. Let's take a look at another process, multiplication and division. Multiplication and division you guys should be fairly familiar with. So if we have, let's bring this back to real numbers. Let's say 1 over 2 times 3 over 4. If you wanted to multiply these, you would multiply 1 times 3 and 2 times 4, which is 8. So I'd get 3 over 8. Now if I took the same thing and I did 1 over 2 times 4 over 3, or sorry, let's say divided by 3 over 4. You should remember that in order to do this, I would essentially flip the fraction, take the reciprocal of the second fraction, and multiply. So this would become 4 over 6, which reduces to 2 over 3. The same thing is going to hold true here for rational expressions. So for multiplying rational expressions, we can multiply the polynomials in the numerator together and the polynomials in the denominator together. If we're dividing rational expressions, we're going to multiply the numerator polynomials, we're first going to invert or take the reciprocal of the the divisor here, the r over s would be the divisor. We're going to take the reciprocal of r over s, and then we're going to multiply. Now, if we can, we want to simplify in this process. So what I would do first is I would simplify the rational expressions. So what we're going to do here is we're going to factor. This is often going to make the multiplication a lot easier. So if I take a look at the first expression here, I have 2a plus 2. I can factor out a 2 to get 2 over a plus 2. In the denominator, I have 3 minus 3a squared. I'm going to factor out a negative 3 to give me a squared minus 1. I'm going to come back to that. I can factor that a little further. For the second expression, 3a squared minus a minus 2. I'm going to try to split this into two binomials. 3a and a being the first term in each. Knowing that I'm going to need one positive and one negative, this would end up being positive 2 and negative 1. If I check this, this is 2a, negative 3a, and together that gives me the negative a as the middle term. So we got to go through some of our factoring processes here. And then in the denominator, I have the difference of two squares. So the difference of two squares gives me the conjugate of the first term, or the root of the first term, 3a, and the root of the second term, 2. So 3a plus 2 and 3a minus 2. Now what I may notice is I have some common factors. I'm going to completely factor this before I start to eliminate my common factors. So this is the same as everything in the numerator being put together. So notice here in our rule, p and r gets put together. So I'm just going to write this as one fraction. The numerator is going to be 2 times a plus 2 times 3a plus 2 times a minus 1. The denominator is negative 3. A squared minus 1. Remember, a squared minus 1 can be simplified into a plus 1 and a minus 1. Then I have 3a plus 2 and 3a minus 2. So what I'm doing here is I'm factoring first because now I can see some terms that I can simplify. So it's going to make the multiplication a little easier. The 3a plus 2 eliminates. The a minus 1 would eliminate. Those would divide each other out and become 1. Now what I'm left with would be the simplified version of my multiplication. So this would be 2 over a plus 2, or sorry, 2 times a plus 2 over negative 3 times a plus 1 times 3a minus 2. And for right now, we can go ahead and leave our answer as such. Now, you could potentially, if you wanted to, distribute this and multiply these out. And so the numerator would become 2a plus 4. The denominator would become a negative 9a squared minus 3a plus 6. I think, let me double check that. Yes, negative 9a squared minus 3a plus 6. And these would be equivalent expressions. For right now, I'm not going to make us, or I'm not going to require that we multiply things back together. We could, but for now, we're just going to go ahead and find those factors and then eliminate those factors as we can and leave the resulting polynomial or the resulting rational expression in factored form. So let's go ahead and take a look at another example. Let's do example B here. In this case, I'm going to move C. Let me just, I'll come back to C, but I'm going to just do B over here. It's going to take up most of this page, so let me section this up a little bit. In B, I have division. So I'm going to go through the same process. I'm going to factor both of the rational expressions. Remember with B, because I have division, this second rational expression, we're going to take the reciprocal of this rational expression. So I'll come back to that. So for 4b, initially I'm going to factor in the c in the numerator of the first rational expression that it has a GCF of m. So that would leave me with 4m squared minus 12m plus 9. In the denominator there, it's a difference of 2 squares, so I can factor this into m minus 7 and m plus 7. And then instead of dividing, I'm going to multiply. So as I factor this numerator, this is actually going to come down into the denominator. I take the reciprocal of the divisor and then simplify. So the numerator has a GCF of 5m, which now becomes the denominator. And I would be left with 2m minus 3. The old denominator, which was m squared plus 4m minus 21, m squared plus 4m minus 21 would factor into two binomials. And this would become an m, first term for each, a positive 7, and a minus 3. If we distribute there, that's how we'd end up getting that positive 4. I can factor just a little bit further, but before I do that, I'm going to go ahead and cancel or divide out some terms. So I see this m plus 7 is the same. So I'm going to divide out that m plus 7 at this point, because I have one that's in the numerator and one that's in the denominator. Now I'm going to rewrite this expression. So the numerator, I'm going to simplify again. So I have 4m squared minus 12m plus 9. This is a perfect square. This would factor into 2m and 2m minus 3 and minus 3. So negative 3 times negative 3 is positive 9. This would give me negative 6m, which gives me negative 12m. So I factored this 4m squared minus 12m plus 9. There's still an m minus 3 that's there, so I'm going to include that in the numerator. Then in the denominator, I have an m minus 7. I have a 5m, and I have a 2m minus 3. So now again, common terms in the numerator and the denominator divide out. So this m in the numerator divides with that m. They are factors. One of the 2m minus 3's will divide with the other 2m minus 3. And what that leaves me with would be what is essentially the simplified version of this division problem. So the result of this division would be 2m minus 3 times m minus 3 all over 5 times m minus 7. None of those expressions could be factored any further, and there's no common factors in the numerator and the denominator, and so this would be the simplified version. So when we multiply and when we divide, we still want to simplify the rational expressions. So we still want to factor. We want to eliminate common factors. The one thing that we have to be careful of is when the problem is a division problem, we have to invert the second fraction and then simplify as if it was multiplication. This is a good place to stop. We'll come back to C as part of the next time we come together in class. As always, thank you guys for tuning in, and I'll see you soon.